Hello students, welcome back. Previously in section 1, we redefined the trigonometric ratios into trigonometric functions. Now that we have functions, let us study their graphs. That's the topic for section 2. First, the sine function. Here's a basic shape. It's a wave function going up and down, starting from 0, 0. Sine of 0 is 0. And we reach the maximum at 90 degrees, or sine of pi over 2. And then coming back to 0 at 180 degrees, or pi, and then go to -1, the minimum, at 3 pi over 2, or 270 degrees. And then at 360 degrees, or 2 pi, we come back to the starting place. And that's the whole period, and the same pattern repeats. Why do we have that kind of situation, or why in the world we have that kind of graph? Well, here is static picture that explains it. On the left, you have a circle picture, a circle of radius 1 here. So sine is y over r, the vertical over radius, but in this case, radius is 1, so the vertical is the function value. So y-coordinate here, the vertical, and this y-coordinate here, the function value, must match precisely. Now, how about this arc length? The arc length is r theta, radius times angle in radian angle, but in this case, radius is 1. This is a unit circle. So this arc length is the same as theta in radian. So this blue arc must match this horizontal precisely. So this point here is theta comma sine of theta, and this program is randomized, so at this moment theta is about 0.67 pi. Run it again, and I'm going to get a little bit different place, still different place, but in any case, please notice that this vertical and this y-coordinate always match, and it's a bit hard to say, but the arc length here and this horizontal highlighted in blue must match as well. This arc length versus this horizontal is a bit hard to see, but this vertical and this y-coordinate, they must match, and that's not too difficult to see because you can see this vertical length and that vertical length are precisely the same, no matter how many times I run this program. Here's the animation associated to that. No, I think I can just run it. Okay, alright. Run. So on the left we have a circle, the unit circle, the circle centered at origin with radius 1. And the angle theta increases from 0 to pi over 2, pi, 3 pi over 2, and back to 2 pi. And then as the rotation goes on, the y-coordinate, the function value of the graph, and then the vertical here precisely match all the time. They must match all the time. And that's how you're going to get the sine function. And of course, this is a whole period, and if I roll it once more, and once more, or backward, you're going to get this infinite wave function. Here's the same graph, but this time from different domain, different viewing window, plotted from negative pi to positive pi. So in this animation, we begin from negative pi, negative 180 degrees, and then past 0, and then positive pi. Let's run it like this. And do you see that the graph is symmetric with respect to the origin? Yes, and that's because the sine function is an odd function. Sine of negative of theta is negative of sine of theta. It's an odd function. So starting from here, if I go left, then we're going to get precisely the same as going to the right, except taking negative, so going down instead. And here's some further properties of sine function. As you saw from the graphs is bounded between -1 and +1, going up and down, between -1 and +1. Sine of 0 is 0 right here. Sine of pi over 2 is 1 right here. Next, sine of pi is 0 here. And next, sine of 3 pi over 2 is -1 right here. And then sine of 2 pi is 0, come back to this x-intercept, and then the pattern continues. That's the whole period. The period 2 pi, so plus or minus 2 pi, will not change anything. If you add just pi, then instead of the same pattern, I'm going down. So we have negative of that. And this one we already saw. And this one is interesting. Sine of pi minus theta is equal to pi. The proof is not too difficult, as a matter of fact. Let's see, sine of pi minus theta is same as sine of negative theta plus pi. And then if I add pi, then I have negative, right? So that's the same as negative of sine of negative theta. And then sine of negative theta is negative, so we have sine of theta. And that's what we have here. So sine of pi minus theta is the same as sine of theta. But this relation turns out to be very, very important in trigonometric equation, especially. So basically what it says is we have a symmetry with respect to the vertical line, sine equals to pi over 2. Let's go to the drawing mode and let me show you that. So let's draw a vertical line like this. Oh my, this is terrible. Let's do it again. Vertical line, and this is vertical line, x equals to pi over 2. And then we have a symmetry with respect to this line. And what does it have anything to do with this? Let's see, one way to see that is starting from here, pi over 2, and then move to the same direction to the right, and also same magnitude to the left. So, not the same direction, excuse me, same magnitude to the left and to the right. And at those endpoints, the y-coordinate, the function value, turns out to be the same. And then that's true everywhere. Starting from here to the right or to the left, either way, function value is the same. That's what the symmetry is talking about. Equivalently, I can start from the origin and then come to the same amount here, and starting from pi, the other x-intercept, and come to the same distance here, starting from pi, and starting from 0, again, the same y-coordinate. Either way, that's what you're looking at. Sine of pi minus theta is sine of theta. It'll turn out that this is very, very important in trig equation. Alright, let's get out of the drawing mode. And Okay, we got out of the drawing mode. Alright, so much for the sine function. Now let's study cosine function. We already went through sine function, so we can move on very quickly here. Cosine function has graph like this, and the outer shape is exactly the same as before, except for one difference. We start from the peak. Start from the maximum, come down to 0, and then minimum, come down to 0 again, and to the maximum. Going up and down, up and down. Compare that with the graph of sine function. Exactly the same, except that the starting phase is different. We start from the x-intercept, we start from the maximum, otherwise the same. And then, if you compare that with the definition of cosine function versus that of the sine function, why do we have the same picture will become really clear. On the left-hand side, in the circle picture, we have the definition of the cosine function. Cosine of theta is x over r, horizontal over radius, but in this case, the radius is 1, so just the horizontal over 1. And this horizontal must match this vertical. And how was a sine function, by the way? Sine function was defined as vertical over radius, and radius is 1. So vertical here must match this y-coordinate value, vertical. So vertical, vertical. Here, horizontal, vertical. What difference does it make? Well, let's go to the drawing. If I turn this a little bit further, then this triangle here will be turned 90 degree or pi over 2 like this, and this horizontal is this vertical here, and then vertical over radius 1, that's sine. So we have this 90 degree pi over 2 phase difference, otherwise the shape has to be exactly the same as that of sine function. Let's look at the animation. We must get out of the drawing mode first. It's a little bit harder to see because we have to see the horizontal versus vertical rather than just vertical, vertical. But you can see that the horizontal here has to match the vertical, the y-coordinate. And then if you tilt the viewpoint and look at it from sideways, then this horizontal will become vertical in the end. Now, the same cosine function, this time pictured from negative pi to positive pi, you can see that the graph is symmetric with respect to the y-axis. That's because cosine function is an even function. So if you move to the left, exactly the same thing as before, just the opposite direction. Consequently, we have the symmetry with respect to the y-axis. Here's a visualization, this time from negative pi to positive pi. Same as before, nothing fancy, just the starting phase is different. And then we have some further properties of cosine. Again, bouncing back and forth between negative 1 and positive 1, and then these basic angles. And then periods 2 pi, plus or minus pi, then the same pattern, or the other side, so we have negative. And the same symmetry as before, but this is not going to be that important, to tell the truth. The symmetry for the sine was really important. And then there are some further properties as well, but those are minor. So much for the graphs of sine and cosine, two most important graphs.